live yet, so
Hi, welcome to our webinar. This is a webinar in a series of webinars we call In Pursuit of the Perfect Transformer. It's part of our 50th anniversary celebration. We thank you for attending, and we hope you enjoy the webinar. Thanks. Thanks again. I don't want to say that too often, but we are appreciative that you're here today on this webinar. It's sound mitigation by design in a transformer. This is part of a series. We have more coming, and we appreciate you attending today. We ask that you take a little time to think of questions during the presentation, and this is on the GoToWebinar platform. So in that toolbox, there's a place for you to ask questions. Go ahead and log your questions in the instant message, and then at the end of the presentation, we will go ahead and answer the questions. As I mentioned, we are celebrating our 50th anniversary. As a part of that celebration, we want to thank our customers and the hardworking employees of our company. Most importantly, our CEO and founder is Prabhat Jain, and he's spent many years with the company. He has a good vision for the company. He's taken it from a small Appalachian-based organization to what it is today. So today we have 4 plants in Chihuahua, Mexico, 1 in Pocatello, Idaho, 1 in Rincon, Georgia, and 1 up here in Roanoke, Virginia, where we're headquarters. We are a one-source supply for power transformers. What that means is we can do about 500 kVA up to about 500 MVA in transformers in all sizes and variances in between. Today's webinar is recorded. We will have this on our website later, so if you want to watch it, feel free to do so. Other than that, without further ado, I'll start into the presentation. So today's webinar is based on a white paper, and the gentleman next to me, Lakesh, authored that white paper, or a co-author of the white paper. Lakesh comes to us with a good degree in engineering from a master's as well out of the UK. He has spent about a decade with Virginia, so that's roughly 20% of the history of the company. He's progressed over many different roles in the company, and he's going to be presenting the white paper on sound. So Lakesh, I'll let you take it from here.
Thank you very much, Brad, and thanks for having me here. And thank you very much to give me the opportunity to present a white paper on the webinar platform. There is something exciting and something new. And telling you frankly, I'm doing this for the first time.
Okay.
So yeah, we've been working on the engineering for a long time. I did my first presentation like really long time back. So yeah, this is something new right now.
Well, I'm sure the audience will be excited to hear from you, and we'll let you kind of partake in your knowledge today. Thanks.
Right?
Thanks,
Thank you. So the question here is, the transformer is a sound or a noise? And anything that we hear, that's a sound. I'm speaking right now in front of you, that's a sound. That's a sound pressure created by the waves, and which is being absorbed by your ears. So, but when this sound becomes kind of annoying or unwanted, then it becomes noise. Now, as a transformer industry is modernizing, substations are being modernizing, and we have more substations in the nearby the residential or commercial area. So that's why it becomes necessary to reduce the transformer noise, and unwanted sound to be reduced, so that it gives the comfort to the nearby occupants.
And then it also would I would think, improve the life of the transformer as well if you reduce the noise.
Certainly it will, and I'll explain you in the next slides.
Okay.
So let me explain you what is sound, right? As it's written here in this slide, a theory of the sound. In physics, the sound is a vibration propagates as an acoustic wave through the transmission medium such as liquid, air, or solid. In human physiology and psychology, sound is received as a wave and then perception by the brain. Speech produces sound. I'm speaking right now, there's a sound, and that's actually a sound pressure. That's what we are hearing right now. And the speech produces sound, and this is produced by practically everything that moves. The frequency of the sound wave is perceived as a pitch, and the amplitude perceived as the loudness. When the sound is unwanted, as I explained to you in the earlier slide, it becomes noise. The transformer during their operation emits noise mainly, and the magnitude of the noise it increases with the size of the transformer. Based on the MVA and the KVA rating, the noise level of a transformer increases. There is a guideline, NEMA TR1, which provides the limits for the specific size of the transformer, and based on that we design. But as nowadays the substations are located in a close proximity to the residential or commercial area in cities, mainly where we have really limited space. So at that particular place, it is become essential to reduce or limit the noise emitted by the transformer. How sound is produced in transformer? So transformer core noise is caused by the phenomenon called magnetostriction. In very simple terms, this means that if a piece of a magnetic sheet is magnetized, it can extend and contract by itself. And transformer is magnetically excited by alternating voltage and current. So it becomes expanded and contracted twice during the full cycle of magnetization. And that means the frequency of core vibration is 2 times the frequency of the current applied. So we apply 60 hertz of current, and the vibration on the core is 2 times the frequency. That means they vibrate at 120 hertz. Right? The transformer core is made from a thin lamination or thin sheets of specially electrical grade steel. And I'll explain that sheet later in the later slides. But right now I can say that those sheets are called CRGO. It's a cold roll grain oriented steel, and they have the lamination, silicone lamination on top and bottom, on the both sides of the steel lamination. Uh, uh, it is made in the way to reduce the losses due to the circulating currents, eddy currents, and subsequently the heating effect of the core. Uh, if the extension and contraction, as described above, are taking place in various directions, depending upon the clamping of the lamination, each sheet can non-uniformly behave over the length and width. And this breathing and twisting motion produces the harmonics of the fundamental frequency up to 16th harmonics. So 16 times the cycle of the current. And these extensions are few micro inches dimensionally. However, they are sufficient enough to cause the vibration as a noise, and this is the core noise. Now let's talk about the other vibrating component inside a transformer. So apart from the core noise, the transformer winding also contracts and expands with the current. And the frequency of winding noise is same as the applied current, like 60 hertz. The noise generated by core and the winding are transmitted to the tank. How they are transmitted? They are transmitted through the mechanical clamps holding the core and coil assembly inside that transformer tank, and also the surrounding medium, which is the transformer oil. The magnetic stilts, if they are used, usually those are used in the higher MVA rating jobs to reduce the losses. So those are also part of the tank structure, and they also vibrate along with the tank and the core and coil assembly, which again add the noise to the transformer. During the operation, transformer generates heat, which is distributed by the oil. And also we use fan to enhance the cooling for the forced cooling method. So fan motors and blades cause the additional noise, and the fan noise is added to the transformer noise, and the total overall noise is the transformer noise during the operation.
So thanks, Lukesh. That was kind of neat on how sound sort of accumulates in a transformer. But I think really it comes back to the reliability and the quality issue of transformers. So I'm curious to see what you have to say about this next topic.
So the quality and reliability of transformer. So let me put in that different way or simpler way to understand. So when transformer noise is generated, it is generated because of the vibration. Due to the magnetostriction effect and the vibration of the core, vibration of the winding, okay, all they come together. Now, when there is a vibration created, and if there is more vibration, what will happen is that the winding insulation, they started like rubbing off against each other. So that's abrasion of the winding insulation. And as the winding insulation reduces, that increases the gap in between the winding lamination. So the pressure is reduced on the winding, and that makes the hardware of the clamping structure loose. So that means eventually there will be more vibration. So we have reduced insulation. So our coils are loose, hardware are vibrating more, and eventually that will lead to the failure of the core and coil assembly. So this is something similar to any vibrating element or any rotating element that we see in our life. Like talk about the car, the same thing. If there is more vibration, you have the loose hardware, and eventually it leads to a failure along the period of time.
But I will admit, one thing in the car, we don't use the word magnetostriction. I like that word.
Yeah.
So that's kind of cool how you talked about how sound is generated and how it creates the noise in a transformer. And I think our audience is going to be interested as well. So what we're going to talk about next is active steps, right? How do you design and manufacture a transformer to improve the output or reduce the sound level? So I look forward to hearing that.
Sure. So, but in order to mitigate the transformer noise, it is essential to know the amount of noise generated inside transformer. With the wide range of transformers that we have designed and number of transformers we have tested for the noise level at VDC and GTC, we have developed an empirical formula to estimate the sound generated by the transformer during its operation. So this is a design stage transformer noise calculation that we do to identify the exact amount of noise what is generated by a transformer. So the transformer noise equation as is given here, it is K1 log W, K2B plus K3. So in this one, the W stands for the core weight, B is the flux density, and K1, K2, K3 are the empirical calculated factors that we use to calculate the transformer noise. So in simple terms, the transformer noise is a function of the core weight and the flux density applied for that transformer. Now, as we talk about that, what amount of noise would be generated, let's discuss about how to reduce those noise. So we'll start with the first thing. The first thing is the core. So core provides the magnetic path or channel for the flux, and these are the steel of magnetic material with high magnetic permeability. As I explained earlier, these are the specially made steel with the layer of silicon on both sides, so that they make every sheet is individual in the construction of the core, and that gives you the magnetic path with the high permeability for the transformer. And transformer core are made with the different grade of material. The basic construction is the same, a CRGO, cold rolled grain oriented steel. However, there are different grades of that, and based on the higher grade of material, we get a higher permeability. No load sound level mainly depends on the magnetostriction and magnetic forces. The magnitude of magnetostriction could be reduced by lowering the flux density. It's the easiest way of reducing the transformer noise. The study shows that reducing the flux density by 0.1 Tesla can reduce the sound by 3 to 4 dB. However, the flux density is inversely proportional to the core weight. So by reducing the flux density, we need to use more amount of core, and that will affect the size of the transformer and the cost of the transformer, because core size is bigger, transformer size is bigger, and that will increase the transformer cost.
So if customers really want a lower sounding transformer, then they probably might have to pay a little more to get that.
Yes, sir.
Okay.
The grades of CRGO lamination, as I explained to you earlier, that which are used to make core, so are the properties such as low losses, high permeability, and low noise generation from the core. When applied higher flux density, or B, and laser scribe lamination, high quality lamination cuts, it is possible to reduce the transformer's noise by 3 dB. Core construction also plays an important role in noise generation. Study shows that the step lap core construction reduces the transformer noise up to 6 dB, and at lower induction with the step lap, even greater noise reduction can be achieved. Well-designed clamping structure and tightening structure and the techniques of the core, the yoke, and leg clamping reduces the noise due to the reduced magnetostriction and reduce the laminar chatter as we are clamping the core laminations, the thin sheets tighter and with the uniform pressure. That will help to reduce the transformer noise. Controlling the three-dimensional undulation of the core assembly will also reduce the harmonics. The vibration of the transformer core sheet is the main source of the transformer noise generation. Tightening of the core and the reducing the gap in the corners will help to reduce the noise. Core laminations are tightened with the glass tips, which are called the thermally contracting glass tips. As you apply heat, they shrink up and they will provide more tightness to the core. and create a very strong bond with the whole structure. The uh, the uh, and also gives the uniform tightening along the core structure, as we also use the mechanical clamps around. Use of non-metallic bolts through the core, and that is really normal in transformer design, that the core is being tightened through the bolt, which means that we also have in the center part of the core, we also put some bolts so that we provide more clamping and less of the bending effect on the core clamping structure, and that's to provide the uniform clamping to the core, and tightened core will help to reduce the vibration, and eventually they will help us to reduce the transformer noise.
Yeah, that's pretty self-explanatory, I think. Yeah. Very good.
Bottom yoke of the core and core legs are stacked, and after stacking, we apply a varnish or wood glue around them. So that will help to fill the air gap, and also help us to keep that core lamination at one place, is tightened together, or they are kind of glued on the edges, so that the edges don't vibrate. Also, that when we have the core construction, then we have horns at the end of the core, and these horns or peaks are really in the air, or on the oil, and they're really free to vibrate because those are not being clamped. So there are two ways of doing it. Either one way is to like cut off those horns, so that like no horns, no vibration. And the second way of doing it is like fill it up that with the putty, so that we can restrict the movement of those horns, and we can reduce the vibration. So in the last few slides, what we discussed about that how we clamp the core structure tightly to make one homogeneous structure, which can make kind of a solid mass, and there is a lace of an air gap, there is a lace of the free or vibrating elements, and that will help us reduce the transformer noise. The whole core structure are uniformly pressurized at every point, and those makes us to have, and those all things makes us to reduce the noise created from the transformer core.
Yeah, so that one component now is sort of isolated or improved, and then there's other components we're going to talk about next.
Yes.
Okay, Mukesh, so if I recall, we just talked about the core, they get the windings, the tank, and the fans. So I'm assuming in the next slide you could talk about the windings.
You are correct.
All right.
So as we discussed about the core, now the second part comes after the core is the winding. And winding also plays a role in transformer noise generation. So let's talk about the reducing the noise from winding. So specific windings noise reduction is achieved by increasing the conductor size or increasing the transformer's impedance. This, however, will increase the amount of copper used in the transformer, and that will affect the cost of the transformer. The other way of doing it, and that is mainly used in the large power transformers, that special kind of transposed conductors are used to make windings. Now, those conductors will help us to reduce the losses of the transformers, and also help to reduce the windings noise. Now, after selecting the material, let's talk about the winding construction. So clamping of the winding, just seems like the core, the winding tightness is also critical, and we assure that we have proper winding tightness during the manufacturing process. So we do multiple drying process, and we do the axial clamping mainly during that. So by drying, we reduce the moisture from the winding insulations. That will help us to reduce all the air gap in the winding, and we can have as much as compression on the windings. Those are at the pre-stage of the winding, and once you make the whole magnetic circuit where the core and the winding are all together, after that the final clamping happens of the winding, which assures a uniform specified pressure on the winding. That will help us to reduce the transformer noise, and mainly the noise generated by the
Okay, great. So core internal, winding internal. Now I guess we're going to go to the tank and sort of the external components of noise.
You are correct, sir. So let's talk about the reducing the noise of transformer through the transformer tank. So first, we know that the more the vibrating element is core and the coil, mainly the core, and those noise being transferred to the tank wall. So the easiest way of doing is like there should not be any connection between the coil and the tank. So there is no connection between them, and that means there is no sound. So that is the easiest way of doing it. But again, we also may have to make sure that transformer is suitable for the transportation, because so that we don't want to damage the core and coil during the transportation as well. So that's why we have to connect the transformer core and coil assembly to the tank. So the other way that we can do is using the vibration damping arrangement between the connections. So if there is any vibration coming from the core and coil assembly, now there is a damper which will absorb the vibration, and then the reduced amount of vibration being passed to the tank wall. And that's how the direct transmission or structural bond transmission of the vibration has been reduced to the tank wall. And now same thing we do at the bottom of the transformer, because transformer core and coil is sitting in the tank bottom. So we can damp the connection point over there. We can damp the connection point on the top, and that makes the total core and coil assembly or vibrating element damp for the transformer tank arrangement. The other way of doing it is like use the wall sound barrier to reduce the bond noise. So we can use the oil barrier or cushion padding inside the transformer tank, which will help to insulate the transformer's noise and prevent it to spread outside. The distance from the noise producing surface to the tank wall can be adjusted for the fundamental noise frequency to reflect the most of the sound pressure from the tank wall and dissipate the sound energy to the oil. And that is how we can totally, like in overall, we can isolate or we can reduce the noise transmitted from inside our transformer to the outside or to the tank.
Yeah. Okay, so as you mentioned, we had core, winding, tank, now fans.
Yeah.
But there was one more topic I forgot at the end here. We're going to talk about the overall, how do you mitigate sound after you install it?
Yes.
What are the external things you can use?
Definitely. We'll talk about that as well.
Okay.
So reduction of the fan noise. Fan's noise reduction can be achieved with the fewer number of rotors revolution per minute. So that means reducing the RPM or speed of the fan. But that affects adversely to the transformer cooling, as we have less CFM or less amount of air. So that means the effect cooling has been reduced. And in order to compensate that, what we need to do, we either need to use more number of fans, or what we need to increase the size of the blades so that it can cover the more area, and with the smaller, lower RPM, we can still get the higher CFM cover for that. The reduction of fan noise can be achieved through the balancing of the rotating mass. As we know that there is a motor inside which is rotating the fan. So if we balance the motor, that means like we have a good bearing and the stable structure for securing the fan. So the structural bond noise from fan itself can be reduced. Also, we can reduce the fan's noise or fan chattering by providing a proper sturdy mounting arrangement for the fans. And also we can use on the mounting arrangement, we can also use the vibration dampers, so that if there is any extra vibration coming out from the fan, that can be damped through those dampers, and that's how we can reduce the sound effect of the fans to the transformer and the overall transformer. The another method that we use is to locate the transformer fans all around the transformer to reduce and to spread out the noise on all the sides rather than concentrating on only on the one side. Multiple radiator banks and multiple fans. So every bank has fewer number of fans, and that's how we can have the same amount of noise on all sides. Instead of that having, okay, we would like all the fans here at one place. So we have 10 fans and they are making noise at the same time. And so that we have 4 fans here, 3 fans here, 3 fans here, and that's how we can reduce the overall fan noise on every wall, and that will help us to reduce the overall transformer noise, mainly during the FRA.
Okay. So great, we've talked about how we design the transformer to reduce the noise or the sound level. And I'm assuming, when I drive down the highway, I see barriers going up. So I'm assuming once we get the transformer on site, there's things we can do as well.
Yes.
Okay.
So Brad, you gave perfect example for reducing the overall or external transformer noise. Using the sound barrier or sound wall is the base next option for containing the sound within the perimeter and reduce the attenuation to the outside perimeter. And that's what you have seen mainly on the interstates, on the highways, that if you have the residential area, commercial area nearby, there is a sound barrier which will reduce the sound spraying through that particular wall and going to the nearby vicinity. Another way of reducing the transformer noise at the site is to use the vibration dampers underneath the transformer. So the vibration damper will help to reduce the transmission of the transformer noise to the transformer pad and to the whole surrounding structure. So outside the structure, there is mainly 2 ways of doing it, and that's how we can contain the sound level at certain limits that's been designed.
So in summary, focus on the core, make sure you have a good, solid, stable core, windings, there's a number of things you do in the windings, the tank again, and the fans come together. Now you have a transformer that's kind of designed to have low noise. Then you get it on site, there's some things you can do as well.
Yes.
And most of this comes from transformers are now located closer to civilization. Grid modernization requires us to continue to upgrade our grid. And so we see this sort of, as you mentioned, you're sitting outside, you don't want a transformer making a lot of noise next to you. So there are a lot of things we can do to reduce the noise level. And in essence, this is kind of what you've lived your life doing the last few years at Virginia is how do we make a better transformer? So at this point in time, that really concludes the presentation. So what we'll do next, Lakesh, is let's look at the instant messages, see what our audience is asking, and then we'll take the questions and then go on.
Certainly.
Yeah, so thanks for attending again. Lukesh and I in the room. We also have Parminder Panesar here as well to help answer some of the questions. I'll let Jenna go ahead and ask what questions that have come across the instant message.
Okay, so the first question is, what is the most precise method of identifying transformer noise?
So the most precise method that is actually been researched for and as described in IEEE C 571290, that taking the sound measurement with the set perimeter and having the multiple points mainly around the transformer and at the vertical height of the transformer at 1/3 and 2/3 height, and that's way that is the way how we can get precisely measured transformer noise.
And that's an apples to apples comparison standard gives you how to measure it. Can you repeat the question again?
What is the most precise method of identifying transformer noise?
So that's the picture we showed where you're looking at, you take a certain distance from the transformer and you measure it based on heights that are inside the IEEE standards.
Yes.
Yep.
Can you repeat that IEEE standard you just mentioned?
It's C 571290.
And that defines the height and the perimeters.
Yes, it defines, there is a figure that they have given that how to take the measurement of the transformer noise at OA rating and FA rating, at how to set the parameter or the data points around the transformer, and at what distance from the transformer. Because if you put your microphone right next to a transformer, it will give you that really high noise. So you need to follow that guideline. Now this question that I'm also confused on that aspect, that and mainly this from customer, because couple of customers, they also ask like we need to get octave band frequency of the transformer, because what we do is a general A-weighted value, which is dBA measurement. But if you're talking about the A-weighted and the Z-weighted, then sound measurement for human ears, that's the base method is to do the A-weighted. So it's a dBA measurement. Z scale or octave band frequency at Z scale, that is mainly help you to identify transformer's noise at which frequency it is giving higher value. So it is just to identify the frequency correlation to the sound.
Yeah. And that octave band is generally used for research and development processes. Of course, we have some customers who want to do octave band, and we are able to do it, but it is quite a bit extra work for us to do the same test.
Yeah.
Whereas for human ears, it doesn't
Right.
make difference
Okay.
what you hear. Yeah.
Right. So the Z rating is pretty much every single noise band that's being created.
Yeah.
Okay.
At various frequency levels.
Got it.
The next question is, what should be the ideal noise level for a quote unquote good transformer?
Okay, now that is, I'll guide you to the another guideline for the transformer, which is NEMA TR1. So NEMA TR1 guideline gives you the exact sound level or the limit of the sound level based on the size and the kVA rating of the transformer. So again, like the quote, the definition of the good transformer noise, that is based on the how you hear the transformer or how you take the transformer. So I would go with the NEMA TR1 rating on that particular aspect.
So NEMA TR1 is the baseline. So good or bad, but that is the defined baseline. Some people want it to be further lower than NEMA TR1. We have to design it, manufacture it accordingly, but that all has to be taken care upfront. So depending on customers, if they're putting right in the hospital or closer to some population, they want a lower dB. If you're sitting out in forest, nobody really cares whether they're making 70 decibel sound or 75 or 80. So it goes back to the customer and the locality where it is going.
And it also goes back to, I think, what we talked about earlier was the lower the sound, perhaps the higher quality of stuff, the more material goes into the transformer. And so it's a matter of, do you want to pay the price for reducing it? Now, is there a correlation to sound and reliability? I mean, can you get to that point where you say, hey, at the NEMA TR1, I'm sure is a threshold of this is a good transformer. Can you say, I don't know, I'm putting you on the spot here about, can you quantify the sound and the reliability part of it, or
there will be some relationship, but no direct relationship.
Okay.
Because the life of transformer is life of insulation, and vibration will add only little to the insulation life or take away little from the insulation life. So this is the effect of core and other metallic parts which are inside, and how we are controlling vibrations on them. Whereas life of transformer, this plus majority of life is determined by the life of insulation.
Okay. Go ahead, next question then.
What will be the scenario of noise generation in case of conventional and bell tank design transformer?
Conventional and bell type?
Conventional and bell tank.
Bell tank. It's not a whole lot.
There is no. Like talking practically, that there would be no difference between the bell tank transformer and the general normal tank design. The main reason or practical reasoning that I can give you is that when we measure the transformer sound we measure at the 1/3 height. And when you talk about the bell shape ends right at the 1 feet height from the bottom of the tank. And usually for the 50 MVA transformer, that's not close to the 1/3 height either. So that's why it will not help much. The bell shape construction is mainly designed to reduce the effort of the manufacturers to when they have the really low head for the transformer lowering it down, like the untanking height. So that is mainly based on the manufacturer's design criteria. Not for the sound.
So sound, it won't make any difference. It's mainly for manufacturer and the servicing aspect of it.
Okay. With noise concerns becoming more and more important, do you think this application would benefit from using electronically communicated fans that can be speed controls via temperature, pressure, etc.?
Now, that is something good, and again, that for that we need to do further research. I have, particularly me, I have not worked on that so far, but again, that's a good idea or a good method of reducing the transformer noise. But again, the transformer noise comes to at the max loading and max rating. So anyway, like we always go with the worst case scenario where you have the full transformer working and you have the fans speed at the max level, and that's where we design the transformer sound for.
And one more thing which will make it very complex is, fan design itself will become complex. We don't have variable speed fans today. So under the version today, ANSI gives you two fan ratings, FA1 and FA2 ratings. So FA1 you have half or some limited number of fans working, and FA2 you have all fans working. If you want to correlate the throughput power from transformer and the speed of the fans, probably better is to regulate the number of fans running. Then you don't bring another aspect of radiation. So if you had transformer 10 fans, you could run 2 fans at one time, so running 5 fans in the FA1 stage. So that possibility, that probably I see more possibilities than going to variable speed fan.
So again, going back to this accumulation effect, right? So
yes.
more fans at lesser speed or fewer fans at a higher speed. And then to your point, I'm assuming as a fan gets at a higher speed, it produces more noise.
It produces more noise, but see, it all depends how much you have to, design and bring more complexity into the product than simplifying by just the switches.
How about, because by technology, can you have a low sound fan? Fan that operates with a low sound.
There are fans available, and we use those fans for specifically very low decibel requirement. There are fans which by nature of the fans, by the design of fans, they make lesser noise. Right. So that those options are always available, but when we go to 10 decibel below NEMA, 15, 12 decibel, we opt for those kind of fans. And everything which we say, every decibel lower comes with extra price.
Yeah.
So.
Good.
Okay. Do transformer noise mitigation methods impact efficiency?
I don't think so. No. The transformer mitigation method does not affect efficiency because the primary design is based on the transformer efficiency, transformer requirement by the customer. The noise is a secondary part which comes at the later stage. And as I told you that when we try to reduce the transformer noise, we play with a couple of design parameters like the core, the flux density, current density, winding design, the core construction, fan, cooling design. So all these factors are added to that, and because of that, we will not have any effect on the transformer life.
No, I think the question was on efficiency.
Efficiency could become a byproduct of reducing sound. Could become, but it will not happen all the time, because if you reduce flux density, you have choice to go to the grade which can have a higher loss. So you'll offset the cost there. But if you reach the minimum where you have to, you probably will get. But there's no correlation of it.
Okay. We had somebody ask if we could go back to the screen with the presenter's name.
Oh man.
We don't have a screen with the presenter's name on it. Sorry.
It's a location.
No, we did.
No,
I'm sorry. We did. Yeah.
Profile.
Yeah, you had his bio also.
That's right. I forgot about that.
Fills up the whole screen. Yeah.
You just want to see the picture, or
It
That's
just
good.
asked if we could go back.
There you go.
Go to full screen.
Well, I hate to do that.
So today's webinar is based on a white paper.
Okay. The next question is, are there any methods of noise reduction by using special synthetic or ester oil as dampening material?
Can you repeat the question, please?
Are there any methods of noise reduction by using special synthetic or ester oil as dampening material?
Okay. This is somewhat similar to the question that we had yesterday, that would there be any effect by changing the oil to the sound? So the basic theory of the sound transfer has the density of the surrounding as a factor. So if you have higher density, you can reduce the transformer noise or transformer noise transfer. However, in the transformer, when we talk about transformer, when it is in operating condition and mainly at the max level or the max FA rating of the transformer at a time, there is the heat factor or the temperature factor comes into the picture, because any material or okay, sorry. So any when the temperature affects the oil, so that means what happened that the molecules of the oil will gain the heat, and because of heat gain there will be a kinetic energy, so the molecules will travel faster than the normal speed, and as they travel faster, they will also take the sound with them as a faster level. So at that higher temperature, the density has really low effect, and then the molecule speeds are taking the transfer noise out. So with the change of the density of the oil, you will not see much of an effect when it is working at the full load.
That's about it.
There are more. There's one more. Okay. It says this presentation was great and informative. Thank you. The question is, will the slides be shared with attendees and?
Yes. Yes. Was there one more on the harmonics?
Oh yeah, sorry. It says which harmonic of noise has the highest magnitude in transformer?
Okay, so answer to that question is mainly the lower harmonics are more severe or having the predominant nature to the recipient or for the hearing. The main reason is that if they are at the low pitch and they travel further into the distance, so that's why I say that at the lower harmonics.
So no,
they have a range.
no lower harmonics, because they have higher amplitude, they travel longer distance, and they are more prominent to the human ear.
Is that good? We're done?
Yep.
Okay, yeah, that's what I said. No. All right, so yeah, thanks everybody for attending. Again, the recordings will be on our website, and we'll share these with anybody that wants them. So appreciate it. If you have any more questions or concerns or needs from us, please reach out to us. The website is here, and you can reach out to us on that email address as well. Thanks for attending today.
Thanks.
Thank you.